Hi, everyone. I think it's a small room, so I won't be too loud. Yeah, so today I'm going to talk about Redbelly. This is a layer 1 blockchain out of Australia. And I'm going to explain why it's a blockchain made for the real world. I'm a professor at the University of Sydney in Australia, and also the founder and chief scientific officer at Redbelly Network. Oh, I think I'm going too fast. All right. Full disclosure, I received funding from the Ethereum Foundation's Redbelly Network. I'm an employee there, part-time. Algorand Centers of Excellence. I also work with CSIRO, the Commonwealth Science Industry Research Organization in Australia, Data 61 for the computer science part. I received funding from the Australian government through the Australian Research Council, and finally I was an invited professor at the Swiss Federal Institute of Technology in Lausanne for some time, and so the things I'm going to present today have been funded by these different partners. Once upon a time, we came up with a blockchain technology that was a revolution for all of us, and we hope that it's going to disrupt the life of other people in the future. This was super exciting, but since then we have seen a lot of hacks happening, right? And some of them are just double spending, something that is very simple, which results from the lack of consensus, like nodes of a distributed system not being able to agree on a unique block at a given index of the chain. In which case we have forks, so multiple blocks, and if these blocks go undetected for long enough, then that translates into a double spending attack, which is essentially stealing assets from the blockchain. So among the double spendings that we know of, because there might be many more than what we heard about, at least we know that Bitcoin Gold, Ethereum Classic got hacked through double spending, right? So this is a problem that might happen in the future, and we have to keep that in mind. Okay, and what came out of Ethereum back in 2015 and Vitalik is the functionality of decentralized application through the use of smart contracts. So it was going much further than just doing the classic scripting language of Bitcoin and not just doing transfer, but coming up with this generic application that would allow us to do pretty much anything we wanted. So the problem is that this decentralized application in an non-accountable world would be hacked as well, right? So you remember probably the DAO attack where essentially 150 million US dollars got stolen. And then there were other hacks as well happening. More recently, there was the Upbit hack that happened on Solana, which is an exchange that occurred exactly 6 years after a previous act from also North Korean organization, as it seems, on the exact same exchange that was running on Solana, right? So it's something that is common, that happened again and again and again, and it looks like it's going to increase in the future. We're going to have more of these hacks happening on decentralized application and smart contract. And I believe that the core problem here is that we have a lack of accountability. We don't know where it's coming from, and usually the hackers will get away with the loot and it won't get caught. This technology has been so interesting that we've been having a lot of fun breeding CryptoKitties, for example, on Ethereum back in 2017, 2018. That was a big thing, like people were breeding them, exchanging them. That was funny, right? That was really a funny application. And but it also turned out to congest Ethereum, right? And at that time, there were so many transactions that actually you had to wait a long time for a transaction to get in, or you would have to offer a very high transaction fee. That was the beginning of the scalability problem that we started observing. Too many people wanted to trade them. The problem is that we started going into L2s. We started saying, okay, you know what? Blockchain is too slow. Let's do things off-chain, outside the blockchain. Which is, it defeats the purpose of using the blockchain in the first place, because then you expose yourself as to security vulnerability if you do things off-chain, right? And that's not the solution, right? We don't want to do things off-chain. That's not the purpose of blockchain design. Another issue that happened is the money laundering. You might say, oh, it's not a real problem. But actually, if we really want to democratize the use of blockchain technologies, and we want to talk to trade finance, for example, we have to solve this problem. Because if the people are anonymous, and they can launder their money or finance terrorist attack, then it's not going to be used in a regulated environment, and the real world users will not jump in, right? So we really need to solve this accountability problem also for this reason. Another problem that that my research group came up with was the availability of Solana. They looked at Solana in particular. It was very popular last year when Donald Trump decided to launch a meme coin on it. I think a lot of people have launched meme coins on Solana. It's very famous for that. The problem is that it's barely available. If you think about a distributed system, its property is supposed to be available despite the failures of some of the nodes of the network, right? That's one of the key principles of distributed systems. The problem with Solana is that between 2021 and 2023, the amount of outages that it experienced led to an availability that is lower than 2 nines. That's not much. To give you a context, a cloud computing platform would offer at least 3 nines availability, which means it would be up and running 99.9% of the time. So having a distributed system that is not even as good as cloud computing, that's a bit of a problem. And we have been talking to people who do proper research at Solana, in particular the head of ENSA research, and actually they came up with some paper indicating that, yeah, Solana has some dramatic problems. Actually, in their paper, they showed that a single malicious user could break the Solana system, right? So they're working actively on trying to improve that, which is great. But the first instance, the one on which Trump launched its meme coin, is not super available. Since then, we have made some further progress. Stable is a framework that allows people to compare the fault tolerance of blockchain technologies. This is open source. This was published at Middleware 2025 last year. I think, if I'm remembering correctly, and we got the badges for the fact that it's all the experiments that we ran, where we tested Algorand, Solana, Avalanche, Aptos, Redbelly, among others, are reproducible results, right? So you can reproduce these results. Of course, before publishing this paper, we informed the security teams of this blockchain saying, hey, we found a way to crash Solana and Avalanche. Take a look at our paper. But then it got published, and it indicates under which condition and what type of failure you need to inject in the distributed network of Solana and Avalanche to crash them. But there are other attacks related to partitioning, message delays that we have run using this framework. So I encourage people to use it if they want to test the fault tolerance of their blockchain. And I believe that, and that's what I'm going to argue in this talk, is now things are changing, right? We really want blockchain not to be something that's going to be used for toy applications, but something that's going to be used for the real world. What do I mean by that? For those who know, it relates to RWA, right? We would like to make sure that we can tokenize real-world assets on these platforms. And for that, we need to change and improve the security of these systems. So when we talk about real-world assets, what do we talk about? We don't really talk about meme coins or crypto kitties anymore. We talk about currency, commodities, like things that exist in the real world, but that have a digital representation that we can put on a blockchain. Just as an example of commodity, at Redbelly, we have tokenized titanium that was taken out of the ground in South Africa and tokenized immediately on our platform so that it could be traded before it was shipped and sold physically to the US, for example. But we also tokenized securities like private company shares and other types of securities. What I want to say is that for the traditional finance and a lot of companies of the real world to really use this technology, we have to make it secure, and we have to make it accountable, and we have to make it scalable, and we have to solve all these problems. Right, so when we're talking about real-world assets, we're no longer talking about things of low value. We're talking potentially about your mortgage, your real estate property, or even your pension, right? And you don't want to mess up with these things. Okay, so here comes Redbelly. Redbelly was designed to improve the security of the blockchain technologies, but it uses the Ethereum virtual machine inside it, right? So anything that you can write and works on Ethereum, like that is written in Solidity, and then compiled and uploaded, can also be uploaded on the Redbelly network, right? So same thing, the bytecode will be executed in the same way. It's just that it's done differently because it's Redbelly. So there is no forks. It's open, permissionless. There is instant finality in the sense that we don't fork. So each time you see a transaction, you know it's there for good. You don't have to wait for conflicts between different branches to be resolved. There is built-in regulatory compliance in the sense that we're identifying. So every single user who wants to join our network will have first to go through an identification process with an identity provider of their choice in the jurisdiction that they want. But this will allow the public key to be registered in our system. We're still considering ourselves as permissionless because Redbelly will never cherry pick anyone. It's just that only human adults can be users of Redbelly network, right? So an AI bot will not be completely autonomous. There could be an AI bot, but it will be handling the assets of a real human that will be accountable for him, okay? Finally, we have a fixed gas fee, and we believe this is very important for businesses. In general, they have a budget, and they need to know how much money they will pay for how many transactions, right? If the fee varies with the volatility of the coin, then that becomes a problem for the businesses. And finally, as I said, it's EVM compatible. Okay, so why is it, how can I convince you that it doesn't fork, right? That's gonna be hard, given that a lot of blockchain forks, and sometimes when the consensus has been proven by the best research scientists, it turns out that there is a flaw in the proof. So, of course, we've done the scientific proof of writing 10 pages by hand, saying, yeah, our consensus protocol solves the consensus problem. But that was not enough, right? So we decided to go one step further. So what we've done is we did formal verification using model checking. In this particular instance, it's even parameterized model checking, which is better. But anyway, we took the source code or the pseudocode of our algorithm. We used a methodology that was published by some of our colleagues and co-authors in order to come up with a threshold automaton, which is a mathematical representation of the algorithm. When you do formal verification, you have to make some fairness assumption. Like if I visit an infinite amount of time this state in my threshold automaton, then I will explore all the outgoing edges or the transitions out of this state. Using this fairness assumption, we came up with a simplified version of the threshold automaton. Here, we reduced the number of edges and nodes, which allowed us to feed a model checker. And we also gave to this model checker the consensus problem formalized with linear temporal logic. At the end of that, the model checker could output that DBFT, our consensus protocol at the heart of Redbelly, was solving the consensus problem in all possible executions and for any system sizes. So the fact that it works for any system sizes comes from the fact that we use parameterized model checking. So it tells us that DBFT solved the consensus. It means that when we have a block, we know that all the nodes of the network agreed on the uniqueness of this block. There is no other block that competes. There is no fork, right? And what I wanted to mention as well is that it's deterministic and it doesn't assume synchrony. So without going into the details, I believe that determinism is the key, because if you have a consensus algorithm that is probabilistic and that fails with epsilon probability, you can make epsilon as small as you want. The problem is that eventually you're doomed. Your blockchain will fail. Why? Because each time you add a new block, you have an epsilon chance of failure. So if you look at an infinity execution, the probability that it fails is 1. You're guaranteed that it will fail. Okay, so determinism can bypass this issue. We published that in the most important distributed computing conferences, PodC and DISC, and we did that, I have to acknowledge, with experts of formal methods, because I'm not, right? So people from France, Austria, and Switzerland, and the US, my former students, who did this work. Otherwise, I wouldn't have been able to do that myself. We also came up with a solution for accountability. We called it polygraph, because essentially the idea is that it detects lies. Each time someone is trying to equivocate in a distributed system, it has to send different messages to different honest participants. And by requiring to sign every single message that are important to the consensus, what we can do is we can build an undeniable proof of fraud by just concatenating the conflicting messages. For example, if you say 1 and 0 to different people, if they exchange this signed information, then there will be a cryptographic proof that you have lied. So this accountability is very important because if someone tries to double spend, then we can punish them. In some sense, we can come up with a deterrence technique so that we never have to punish them and they will always behave. Okay, so this is the polygraph paper. We did a zero loss blockchain, which was a blockchain that could tolerate a majority of failures, with Alejandro, who is in the room as well. That was back in 2024, and we received the best paper for that. And finally, in 2026, there is an upcoming publication that is accepted at IEEE Security and Privacy, which is the flagship scientific security conference, where essentially we make accountability scale to very large networks. Another aspect, and that copes with the congestion, is that we made blockchain collaborative instead of competitive. So if you look at classic blockchain, there is a competition there. Everyone is trying to impose its block to the rest of the system. The problem when you do that is that regardless of the number of proposers or validators that you have in the network, you will always only append one block and you will discard the others. Instead, if you can be collaborative, what you can do is you can group all the valid blocks that are proposed by different validators, and you can put them in a super block and append this super block. By doing that, the number of transactions that you can commit per consensus instance grows linearly with the number of proposers, and this is true scalability. So in some experiments, what we've done is we increased the number of machines, and we looked at the number of requests that could be committed per second, the throughput. And what we could see is that the number was going up as we were adding more proposers because they were proposing more blocks and the super block would become bigger and bigger. Of course, it flattens at some point because of the limited network bandwidth. We published that again in IEEE Security and Privacy. That was back in 2021. And we did a benchmark that is open source that allows you to compare blockchains in realistic environment by running realistic applications. And you can test the performance and you can compare with other blockchains. It has been reused by some of our colleague researchers for testing other blockchains. What is interesting is that ChainSpec, a company completely separate, has reported some the best performance they could see in production on layer 1, and also there are some layer 2 blockchains. So blockchain technologies, let's put it this way. And what they said is that they looked at their mainnet and they looked at the number of transactions that were committed per second on mainnet in production. So even though theoretically Redbelly has more than 600,000 transactions per second as per our lab experiment, in practice we could only commit close to 100,000 transactions per second on mainnet. When you look at the one block metric, which compares 2 blocks essentially, or 73,000 with 100 consecutive blocks. Anyway, that was the fastest blockchain that they ever seen in production. So that was pretty cool, and it was even faster than some of the layer 2 in production. Another things that we wanted to do was to make sure that there is accountability, and for that, what we had to ensure is that every single user would first identify themselves through an identity provider before they could enter the Redbelly network. Okay, so these identity providers are separated, decentralized, but they register the public key so that the user can access the network. And this is also very important to cope with malicious attacks like front running, maximum extractable value, sandwich attacks, but also money laundering in general. What we've done is we published a paper that was accepted and published at DSN in 2024 that shows that it's an algorithm, I won't go into the detail, but allows you to maintain an order. So the transactions that are arriving to correct node in a certain order will not be reordered at execution time, right? So it prevents front running, back running, and sandwich attacks. And I wanted to touch on the resilience also of our blockchain because I talked about Solana and SLA and availability. You might know that Google Cloud offers 3.9 availabilities, 99.9, right? So what happened is here in last year, it had a global outage. And what we realized is that that was not an isolated case. In October, AWS had a global outage as well. Even though we're running on top of these cloud providers, the number of active nodes remain above, or access points remain above 95, right, at all times. So Redbelly, since it has been launched 15 months ago, has been up and running 100% of the time. I'm just going to finish and wrap up. We've done some, we have plenty of partners right now. We're in production, as you can imagine. And I wanted to conclude by saying that it's secure, scalable, accountable, regulated, and resilient. And if you want more information, you can go to this slide and scan the QR code. Oh, I think it's off. Thank you very much.
We have time for one question, if someone has a question.
I was wondering how addition of public keys of the user happens. Who is this central authority that manages it?
You can do it yourself. It's just that once you have one key that has been registered by an identity provider, then you can access the network and say, hey, you know what? I want to create more wallets. And then you just add them to your account. I mean, nobody will make the link between them, but you are entitled to create new address if you have one address that works. So as many wallets as you want. There might be a physical limit on the number of addresses. So it's not as many as you want, but yeah, you can have multiple ones. Thank you.
Thank you.